All right. Good morning, everybody. Hope everybody's doing well. We are on our next lesson. We are talking about Unit 8, and we are looking at our first day of parametrics in Unit 8. So, parametric equations and how we do calculus with those. So, in our first day with parametrics, we're just going to kind of mostly do a recap of what parametric equations are. Um, what they look like, what kind of math we should already know how to do with them. So today's kind of a review day of parametrics. So if you had the opportunity to learn about parametrics in pre-cal, a lot of this will look familiar. And then the next day, the next lesson, we'll be able to do more calculus stuff with parametrics. So here's a cool little warm-up practicing yesterday's lesson on surface area. So maybe take a second and try this, and when we are face-to-face, we should have enough time to be able to do this warm-up together. So, I included this in the notes as well. You don't have to worry about doing it if you don't want to, but I just noticed that sometimes coming up, we're going to have some more exact value trig, and I figured a little bit of practice wouldn't hurt. So if you would like to try to work on this, you're more than welcome to, but just, again, some more practice. But anyway, let's jump into parametrics, okay? What exactly a parametric is. So a parametric tells you a position. Okay, so I'm going to write this out this way. I'm going to give you kind of the formless definition here. So a parametric equation. It tells you your x and y position at a given parameter. And that parameter is usually denoted by t, but it can be other than t sometimes. Usually it means time, but it could be more variables than just that. But basically what I'm saying is we're introducing a third variable almost. So something to kind of keep in mind here is if we have something that's like not a function. Okay, something's not a function. We can't write it. We can't write as y equals f of x. Like for instance, like something like this. Okay. Notice I'm drawing some arrows along the line here because I'm talking about a specific direction. Well, there is a way that we can write it using a parameter. And so instead of having like y equals f of x, we'd have something in the form of like x equals f of t and y equals g of t, where t is just my parameter. Okay, so it's like we have two equations, okay, where t is a parameter. It's usually time, but it's not always time. Okay, so whereas with what we were doing like in what we call rectangular math, like when we have like x and y coordinate planes, that's just written as x comma y. Now when we're doing coordinate points, we're going to have something a little bit different. So with parametric, we're going to have like f of t and g of t. Okay. So we're going to be able to tell our position. So as time moves forward, so like as time goes, like, you know, time equals 1, 2, 3, 4, it's going to be telling us our position at each particular time, and we move along a specific path. Okay. So I got plenty of examples for us to look at that, but that's ideally what a parameter is. I like this next example that kind of explains or gives an example of a parameter. So, for instance, like some functions, some parameters can be written in different forms. Like I love this example. So, a single curve may be described by several different pairs of equations, with each version being called a parametric curve. So, in this example, we got two sets of parametric equations for the quarter of the unit circle in the first quadrant. So it describes the same curve, but does so in like a different direction. For instance, here is one way to describe the unit circle as a parametric. So if we look at our parameter being between 0 and 1, if I plug, like, for instance, if I plug like 0 in for t, let's say I plug 0 in for t, then I get x equals 0, and I get y equals the square root of 1 minus 0 squared, or 1. So at the parameter of time equals 0, or t equals 0, my position is at 0, 1. So here's the point 0, 1. If I were to plug in the point, say, 1/2 in for t, so you can kind of see what they're doing. I plug in 1/2 for t. I have this position. If I plug 1 over the square root of 2, I have this position. So as t gets bigger and bigger, this is the direction I'm going in. We can draw arrows to denote that. Okay? So plugging in different t values is going to give me different points on the unit circle. And here is the exact same curve described with a different set of parameters. So like I'm using the t values between 0 and pi over 2. And honestly, this is the way you're used to seeing a unit circle being drawn. And that is a parametric equation. So like if I plug 0 in for t, I'm going to be at the point 1, 0. If I plug in t equals pi over 6, I'm going to be here. If I'm going to plug in pi over 4, I'm going to be here. Pi over 3 is here. So in this case, it's the same parametric curve, but it's being drawn in a different direction. Okay? So, I mean, look at the note right here. Each has the same graph, same set of points. The one on the left is traversed clockwise as t increases, and the one on the right is traversed counterclockwise. And traverse just means travel. So parametric curves are cool. They're interesting. They draw a curve depending on what your parameter is. Let's look at an example of graphing one. All right, so I think this will be able to really clear things up too. So it looks like we got x equals 2t minus 4 and y equals 3t, or 3 plus t squared. So let's create a table of values and graph what's going down. Okay. I'm going to do 4 columns just to explain something. You don't always have to do 4 columns. I'm going to do 4 columns here. We're going to start off with what we're going to let our parameter be. Okay. I'm like, usually they're going to like give you some type of domain for t. Okay. Usually they give you some domain for t, and if they don't, usually it's a fair point to start at 0. So like, just to be sure though, I'm going to go back one. I'm going to do 0, 1, or -1, 0, 1, 2, 3. Those are the points I'm going to do. And again, usually the t values are given to you to where to start, but that's how we're going to start. All right, we're going to figure out our x position at each given time. And we're going to figure out our y position at any given time. And then I want us to just write it as a coordinate point so we can graph it. Okay, so for instance, if I plug like -1 into that, and you can pause the video and do this on your own. It's nothing more than plugging the t values in for t and your x equation and your y equation. But I'm getting -6 and 4. So the coordinate point is going to be -6, 4. If I plug 0 into this, I'm getting -4, and I'm getting 3. And you kind of get the idea here. If I plug 1 in, it's -2, 4. If I plug 2 in, it's 0, 7. If I plug 3 in, it's 2, 12. And you can take the time. I don't feel like I need to finish the last column, really. Okay. So, let's graph those points and see what happens. So let's graph the first one. The first one's at -6 up 4. It's right here. So that's the point at t equals -1. At t equals 0, we're at the point -4 up 3. So we're right here. Then we're at -2 up 4 at time equals 1. At time equals 2, we're at 0 up 7. At time equals 3, we're over 2, we're off the graph. So if I were to follow this parametric curve, I'm going in this direction here. And usually with parametrics, we can draw arrows to show which way we're traveling as t increases. So this parametric curve looks like some type of parabola almost. We can describe it in terms of x and y and based off of some parameter. In fact, we are able to figure out what the actual rectangular graph is, and it's pretty easy to do. Okay, so like right now, this is in parametric form. This is describing some function with a parameter t. But if I would like to know what the rectangular version is, or the f of x, or the y equals equation, I'll just call it the rectangular form. It's not terrible at all. We can eliminate t. And if we eliminate the parameter t, we're left with a rectangular equation. So um, let's think of it this way. We got x equals 2t minus 4, and we got y equals 3 plus t squared. If you want to get the or eliminate the parameter, you're trying to get it in terms of just x and y. So the idea is really just to get t by itself for one of them and substitute it into the other. And usually I try to keep it as y equals, but it just depends on which one's easier to get t by itself. And I think it's easier to get t by itself on this left equation here, right? We can add 4, and we can divide by 2. So we get 1/2 x plus 2 equals t. And then I can take this t equation here and plug it in for t up here. So I'm getting y equals 3 plus 1/2 x plus 2 squared. And that's the rectangular version of what I have up there. Now let me simplify this just a little bit so we can kind of see what's going on here. I think you'll find this is pretty interesting. Just trying to make a little bit of a point here. Like for instance, if I took out a 1/2 as a GCF, just kind of bear with me here. First of all, I'm gonna move the 3 over right here. So I'm gonna have 1/2 out of the distributed out of this binomial. I'm left with x plus 4. And then if I take the 1/2 out squared, y equals 1/4 x plus 4 squared plus 3. And the only reason I'm doing it this way, and you can expand this if you want, or you can just leave it this way. I don't care. I mean, the point I'm doing this is to just show you that this right here is a quadratic, and this is a quadratic in vertex form. I know we're used to dealing with standard expanded form, but this is vertex form, and the reason it's in vertex form is because it tells us what our vertex is. If you remember, these two numbers are our vertices, so our vertex is at the point -4, 3. And if you look up top here, our vertex of this parabola here is right here at -4, 3. So just the point I'm trying to make is that if you want to change it from a parameter back to a rectangular equation, you can. It eliminates the parameter, so it kind of eliminates that direction, but it does graph the same exact equation with the same exact shape. Okay. All right, cool. We just did this example a second ago. So we eliminated the parameter t in that last equation. And just a refresher, we got y equals 1/4 x plus 4 squared plus 3. And you can also write that in standard form. And if you do expand it, I got 1/4 x squared plus 2x plus 7. Both are fine. But both of these equations describe a quadratic function. One just does it with a parameter t, and one just does it with x and t, or x and y. Okay, now let's move on to this next part. This next part is pretty cool because it's talking about another parametric equation where the parameter isn't t, but the angle, theta. So our position depends on what angle measure we're at, not what time measure we're at, which is pretty cool. So this particular type of parametric equation is called circle parameterization. This is whenever you have a parametric equation that is in the form of some type of circle type function, where we have some type of radius r. Okay? Now we know the rectangular version of this to be x squared plus y squared equals r squared. The parametric version of this looks like this. Okay? Another way of saying this is where x is equal to r cosine theta, okay, and y is equal to r sine theta. Very similar to what we would expect with the unit circle. Now, the reason these two are equivalent is because I want you to think about it this way. Like if I ever ask you to eliminate the parameter, okay, if I ever ask you to eliminate the parameter from a circle parameter to a rectangular parameter, it's not terrible. It's not like where you solve for one parameter and substitute the other one like before. It's where you set it up in this form here. So for instance, like if I take x squared plus y squared, just like I did right here, if I'm trying to eliminate the parameter, look what happens. I get x squared plus y squared equals, well, it'll be this term squared plus this term. So that would be r squared cosine squared theta plus r squared sine squared theta. And if I were to take a GCF of r squared out, I would get r squared on the outside, and I'm left with cosine squared theta plus sine squared theta. And we know that this simplifies down to 1 by the Pythagorean identity, and 1 times anything is just whatever you're left with. So we get that x squared plus y squared equals r squared. So if I'm given this as my parameter at the beginning, if I want to take it to rectangular, it's as simple as just squaring both of them, adding them together, and it takes you to that rectangular form. So this is describing a circle parametrically. Let me give you an example of something similar. Let me give you an example of this. Let's say that we had the parameter x equals 5 cosine t minus 1 and y equals negative 3 sine of t plus 2. If I want to eliminate the parameter, if I want to go to the rectangular form, it has to be in the form where we have like if I want to be able to do this logic that I'm doing over here on the left side, you got to have like a cosine or a sine equaling something. Okay? Let me explain. So for this one, this is the same thing as saying like cosine of t equals, I can add 1 and divide by 5. Okay, oops, that should be add 1, sorry. And for this one right here, this is the same thing as doing like sine of t equals y minus 2 divide by negative 3. Okay. And then I can use that logic that I did over here. I can use that Pythagorean identity, cosine squared t plus sine squared t equals 1. And I know what cosine equals, and I know what sine equals. So I can say that this is the same thing as x plus 1 over 5 squared plus y minus 2 over negative 3 squared equals 1. And what happens if I distribute these squares? I'm going to be left with x plus 1 squared over 25 plus y minus 2 squared over 9 equals 1. Does this look familiar at all to anybody? Huh? Take a second. You can do this. It's an ellipse. Now that I think about it, I hope that you learned conic sections. And if you didn't, I promise you, you're not behind. It's just a cool little observation to make. But this is an ellipse. If you were to graph this in Desmos, it's an ellipse centered at negative 1, 2. So like here's negative 1 up 2. And the ellipse extends horizontally at a radius of 5. That's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And it extends vertically up 3. So that's my ellipse. That's the graph that it makes. So if you don't know conic sections, we will review this a little bit together. But the point is that that parametric curve makes a circular type shape. It's pretty cool. So the biggest thing I want you to take away from this side is if you want to eliminate a parameter that is in a circular form, okay, that's whenever you have x and cosine and y and sine together. This is the process to do that. If it's got anything other than just cosine and sine, it's going to be like an ellipse. But if cosine and sine are just by itself, that'll be like a circle. Okay. All right, we'll do plenty more of examples with that. In fact, let's do an example with example 2. You'll see kind of what I'm talking about. All right. I know we just learned circular parameterization. Oh my God, I can't say the word. Parameterization. And that's true whenever we have it in the form of like x equals cosine and y equals sine. So like x equals cosine and y equals sine. Like that's the form of circular parameterization. And if we don't have it in that form, but we have some other type of trig, like, I mean, this is x equals sine and y equals cotangent squared. Well, that's not circle parameterization. We can eliminate parameter just by a normal means of substitution. Okay, so we try to substitute one in for the other. And how you want to do it is like think about look for the more complicated one, and try to get that maybe like all in terms of sine or cosine. Right? Like we know what cotangent squared is. That's the same thing as cosine squared over sine squared, right? Now, I know that x equals sine of t, so why don't I try to get this entire thing in terms of sine? So what do we know cosine thing is? Cosine squared is the same thing as y equals 1 minus sine squared t over sine squared t. So notice that I have all of sine in this equation, so I can replace all of sine with x. So what I got is y equals 1 minus, instead of sine squared, that's x squared over x squared. So there, we just eliminated the parameter. This is the rectangular form of the parametric equation over here. Okay. So we got plenty of practice to being able to eliminate parameters, but it's all good. How about this next one? We just want to get x and y as just y equals x, some type of form like that. We're going to try to eliminate the parameter. So we want to try to get t by itself in one of these equations. Well, if you're trying to decide between the two, let me just give you a little bit of a hint. If you ever have t squared, don't solve for t given t squared. You never want to have t equals plus or minus something. That doesn't make substitution that easy. But solving for t over here is not terrible at all, right? Like if I have e to the t power, how do we get e out of the power? Or t out of the power? Get the natural log of both sides. Right? Take the natural log of both sides. So in this case, the rectangular version of this parametric equation would be y equals ln of x squared. I have to take the ln of x and plug it into t. Okay. And then lastly, same thing. I mean, we got a parametric equation. We got a x equals and a y equals. If I want to eliminate the parameter, I think we want to plug one in for the other. Again, I wouldn't try to solve for t on this side, but let's try to solve for t on the other side. This would be like x minus 1 equals 1 over t. I can multiply both sides by t. So I get t x minus 1 equals 1. And then I can divide by x minus 1. And take this t, plug it up here. So finally I get that y equals 1 over x minus 1 squared. All right, well, we got a little bit of exposure to parametrics. I got one more for graphing, and we can do this parametric together. All right, so I'll wait and hold off. If you would like to try to do it on your own, it told you, do the same chart that we did earlier in this lesson, and it told you kind of where to start and where to end with your parametric equation. I recommend doing intervals of like pi over 2 from negative pi to pi. I think that'll be your best bet for a clear picture. Okay, I'll let you do that on your own, and good luck, and we will see you in class.